Thank you so much for coming on a Friday afternoon in the last session of the last talk. We don't have the licenses to Every Day I'm Shuffling, so I hope you all know that song and you can just play it in your head as we're going through the slides and just keep that going. So, as Paco said, I'm Holden. I'm an engineer at Databricks, and I'm the co-author of the Learning Spark book, which is awesome, I think, obviously a little biased. And I've worked on sort of search and recommendation problems in the past at Foursquare, Amazon, and Google.
I'm Vida. Paco mentioned that I'm a solutions engineer at Databricks. What that means is I support customers that are coming onto Databricks Cloud and using Apache Spark. I first started using distributed systems as a software engineer at Google, where I worked on mobile restrict search and on speech recognition for the voice search project. And then I also worked at Square, working on scaling their reporting system.
Cool. So we made a few assumptions about you as an audience that I hope are true, and if they're not, it's not going to be too bad, but just to clarify, I'm hoping you all know what Apache Spark is. Everyone know what Apache Spark is? Yay! Great. Okay, cool. I'm assuming that you're using it right now or you're going to be using it soon. And you want to understand Spark internals so that you can make your programs awesomer. And by awesomer, we mean more efficient, faster, and really awesome. And we're going to do this by understanding sort of what's going on beyond just the API level and sort of what Spark's doing underneath the hood. And with that,
there are three main things we hope you take away from this talk today. The first is to understand what the shuffle is in Spark, and I'll define that. The main thing is, though, whenever I see a customer write in that they have a Spark job that's running really slow and they can't figure out why it's going so slow, 90% of the time it has to do with something wonky happening in the shuffle. The other thing we'll hope you'll really drill into your minds is the difference between when your code is running on the driver program when it's actually running on the Spark worker nodes. So all the time we see in the Spark user list that people write in with these cryptic errors that they don't understand, and it's usually because they haven't gripped this concept yet. And the last bit, we're always, as software engineers, working to factor our code and write it as beautiful as we can. So we'll go over some tips for that, and hopefully that'll help you reuse your code between batch and streaming, and also just make it easier to test your programs so they're more likely to be correct. Okay, so let's begin. We're going to go over really quickly, I know you've already seen this a million times, but word count in Spark. So word count in Spark, you first get a Spark context, and you're going to run a text file command to read in text files and split them out into lines. The next bit, you're going to do a flat map, and you're going to take each line and you're going to split it into an array of words. And then we're going to go over each of those words, map across them, and output a pair with the word with an initial seed count of 1. And then we're going to call ReduceByKey, where we have two values for counts. We're going to add them together so that what we can produce is the word count. This is just Python word count, and we have word count in well under 100 words in Spark. So super easy to understand. So what I want to ask you guys today is, what would happen if we instead did GroupBy Key? We start out our program the same way. So we're still going to do our text file command. We're still going to flat map that to split that out into words. And we're going to do a map where we output the word with an initial seed count of 1. But this time we're going to call GroupByKey to put all those pairs together. And we have to write a slightly different Lambda function here. In this case, our Lambda function is going to take in a word with an array of counts. And what we're going to do is we're going to just return a pair with the word with a sum of all the counts in that array. So my question is, will we still get the right answer? The answer is yes, you'll absolutely get the right answer when you use ReduceByKey or GroupByKey. So if you had a small sample code with both of these programs and you unit tested them, both of these solutions are going to work. But ReduceByKey is more efficient when you run this on a really large data set. Most of the time it's going to run a lot faster, and even worse than that, there are going to be cases where if you use GroupByKey, you'll get an out of disk problem when your Spark job would have run fine on just ReduceByKey. And if you want to understand this, what we really have to do is examine the shuffle in a lot more detail. And so that's what we're going to do. Let's look at what's happening in word count. These first lines here, the text file, flat map, and map transitions, those are all happening on the same worker node. So once a particular worker node is chosen to read in that text file and that piece of data, it's the same machine that's going to be processing it through all those commands. But when we call ReduceByKey or GroupByKey, what we're asking Spark to do is take all the pairs that have the same word and put them onto the same machine. So that's going to trigger a shuffle in order to do that, because we have to get all those word counts onto the same machine together. So again, the definition is shuffle occurs to transfer all the data with the same key to the same worker node in Spark. Okay, so let's depict actually what's happening in the shuffle step with ReduceByKey. So we start out with those word count pairs that we had where we have the word with an initial seed count of just 1. What ReduceByKey is going to do is it's going to combine all your data so that on each particular partition, there's at most 1 value for each key to send over the network. So when the shuffle actually happens, it's only going to be, on the final thing, there's only going to be 1, at most, 1 key pair for each word on our final reduce node. So we can use that, shuffle that over. We have 3 word count pairs for each particular word, and we can get our final word count, which is 6 for A and 6 for B. Let's contrast this with what's happening on ReduceByKey. So in ReduceByKey, we have all those same initial pairs with the word and initial seed count of 1, but now we're not going to do any combining. We're going to immediately send over all these key pairs over the network. So that's a lot more data that we're sending over the network. And the other thing is also a lot more data that we are going to actually have to store in those final worker nodes. So that's why it's going to take more disks possibly to store those counts. Even though in the end, we can still get our final right answer, A is 6 and B is 6, we can see how that's a lot less efficient. So the bottom line is, good word, try to prefer ReduceByKey over GroupByKey. So why do we even have GroupByKey? Well, the reason is because not every problem that you can solve with GroupByKey can be calculated with ReduceByKey. So an example, the lambda function in ReduceByKey requires that you're taking 2 values and you can combine them into another value that's of the exact same type. Not all your problems can be broken down that way. So in addition to ReduceByKey, you'll also want to look at aggregate by key, fold by key, and combine by key. All of those do some kind of combination step before the shuffle, and so they should be preferred over GroupByKey. So let's look at another example. Maybe you don't think about shuffle when you do Spark SQL, but you do trigger shuffles in Spark SQL as well. So let's look at this very simple join statement. We're going to do a select star from people in the US. That's some RDD that we have. That's pretty large. And we're going to join it with states. That's an RDD, pretty small. In this case, the states RDD it's just a little RDD with some metadata about each state in the US, so only 50 keys. And we're going to join it on people in the US.state equals states.name. If you were to do this and you do .2debug string on this RDD, we're going to find out what the query plan is for Spark to actually execute this Spark SQL command. And depending on how your cluster is configured, you might see one of 2 different types of joins that Spark SQL is going to trigger to do this. The first one might be ShuffledHashJoin, and the second one is going to be BroadcastHashJoin. So on the next slides, what I'm going to do is show you the difference of what's happening between these 2 different joins. With the ShuffledHashJoin, we start out where we have this humongous RDD of everyone in the US, a whole bunch of partitions, clearly a lot more than 50. Then we also have our small little state RDD here. And in order to do the ShuffledHashJoin, we're going to take all of the data from all the RDDs and we're going to shuffle them over and key them by the state name. So there's only going to be 50 keys that we bring into our reduce phase. So what we're going to find is we have a couple of problems. First, this is really uneven sharding. So the state, all the data for California, that's going to be a lot more data than a much less populous state like Rhode Island. And in fact, it's even worse than that. We have limited parallelism. So we only ever have 50 output keys, which means even if you have a much larger Spark cluster and you throw more machines at this problem, which is usually when a Spark job is running slow, that's what a lot of beginners will do, that's not going to speed up your problem here. This is just fundamentally not the right way to join these 2 tables. So what's a better way to do it? It's actually a broadcast hash join. So let's explain what the broadcast hash join is. In a broadcast hash join, what we do is we recognize the fact that this small state RDD is so small that it can actually fit in memory on each of the individual worker nodes on your Spark cluster. So what broadcast hash join will do is it'll broadcast this small RDD to all the worker nodes. And then when you actually go to do your join, that data is already available on each of your worker nodes to finally do your joined output. So in this case, you can see parallelism of your large RDD is maintained. In fact, in this case, you don't even need to shuffle because that broadcast of the RDD was enough to join your two tables. Okay, so now that you know that BroadcastHashJoin is a better way to join your tables if one of your tables is small enough to fit in memory, how do you configure it? You'll need to see the Spark SQL programming guide for your Spark version on how to configure. I mean, in the future, it's probably just going to happen automatically a lot for you. But for Spark 1.2, for right now, what you'll want to do is you'll set the Spark SQL auto broadcast join threshold to be some value that's larger than the size of your RDD that you want to have broadcast. And then you also want to run this small little analyze command on your particular table in the Spark context. And that just allows Spark SQL to know that that table is small enough that it's going to fit in memory. And if you're in any doubt if you've configured it right or not, you can use the RDD2 debug string, which is going to work on any RDD that you have. But there's also the explain keyword that you can use in Spark SQL to do an explain select, similar to any other kind of explain select command that you would see in a different SQL type of server. Okay, great. Let's go over a third example now of shuffle. Hopefully you guys are kind of seeing how to think about it. So in this case, we're going to do a select star from people in California, a moderate-sized RDD, and we're going to left join from all the people in the world, which is a really humongous table. And we're going to do it on peopleincalifornia.id equals all the people in the world.id. So since we're doing a left join, our final output, it's only going to have the number of keys as the number of people in California. So we shouldn't need a really huge Spark cluster to do this, right? Well, let's actually see what happens when we shuffle. So with the left join in the shuffle step, we have our all California RDD, and we have our really humongous all world RDD. In order to do the left join, we actually have to shuffle everything across the network to get all the data before we can get our final joined output. So the dropping of the data doesn't happen until after everything's been shuffled. There's a couple things that is no longer a problem that was a problem in our previous example. So this is going to shard evenly since we're using a random ID and we have a good sharding function. We're also going to see good parallelism. So if you throw more machines at this, it should run faster. But the problem here is that we need a Spark cluster in this particular case that's large enough to support our all-world RDD, even though our final output size, it's more similar to the all-California RDD. So we should be able to be more efficient in our join. So what's a better solution for doing this? We can just recognize the fact that this whole world RDD can be filtered. So we can do something to select all the IDs from all California RDD, and we can use a filter transform to give us only the parts of the partial world RDD that we care about. And that filter step will happen on the same worker node, so there's no shuffling of the data to do the filter. And then we can shuffle and join that smaller table with the all California RDD to get our final output. So this is clearly a better solution because we have less data shuffled over the network and less shuffle space that's needed on disk to store that. Even though we're doing more phases, you'll notice for this, because we're saving that network traffic, this can still run faster. Okay, so what's the tipping point for huge? You must want to know now. The truth is, I can't tell you. There aren't always strict rules for optimizing, and the first two examples I could give you pretty good rules of thumb of when you should use those optimizations. That's not the case in this one. You have to kind of think about the problem. So, for example, if the whole world RDD, if you weren't doing a select star and you only cared about a couple of columns, and they were pretty small, you used columnar encoding, the filter transform, it might not have saved you that much. It might not have been worth doing. You still have to understand your data and its own properties and the shuffle step if you want to optimize your Spark job. What I would like to tell you, though, is most of the time, day to day, you're just going to be writing Spark, so you're not really thinking about the shuffle. When is a good time to actually step back when your Spark job is running slow and to think about the shuffle? And what can we do to monitor our Spark job and figure out when we're likely having and experiencing a shuffle problem? Well, if your Spark job's running slow, the first thing you'll want to do is head over to the Spark UI and drill all the way down until you get to the task level detail about your Spark job. And here you'll see all the individual worker nodes. You'll see a bunch of statistics about it. And these are the things you kind of want to look out for that are likely that you have some kind of shuffle problem. So one is that you have one particular task that's just uncharacteristically much longer to run than the others. So there's other problems that can cause this. You could also just have a bad worker node, right, that's just running really slow. But if you see it's more systematic, that might be one indication. Another thing is, if your Spark cluster is configured the right way, you may notice that that particular slow task is being launched a lot, so you can look out for speculative task. And then third, I would just scan the different shards and see if the amount of output and input to that particular task seems kind of evenly spread across your tasks. You'd like to see that property to show that you have good parallelism and a pretty evenly distributed load on all your Spark workers. Great, so let's move on to our next topic, and that's to understand the difference between when code is being executed on the driver versus the workers. Let's look back at our good old world count again, but this time we're gonna take our word count, we're gonna actually collect it, and then we're gonna print out our final output. So the parts that are in orange, apologies, this didn't come out so well on this particular program. It pops more on my screen. But the output command, the Spark context, and the print output are in orange, and those are being executed on your Spark driver. On the other hand, the things in red, the text file, the flat map, the ReduceByKey, those transformations, those are code that's being executed on your Spark workers. And last bit, the teal is an action, and actions may transfer data from the workers to the driver. In the case of collect, it does. There are other actions that don't do this. So let's take a look at what's happening on Spark when you actually call collect. So here we have our worker, and it has all our different worker nodes on our Spark cluster and a whole bunch of different partitions. When we call a collect, we're going to send all the data and all the partitions over to the single driver so we can collect it. You can write a unit test based on the program before. It's totally going to work great, so you can get all your output and you can verify that you get the right answer, and it's going to work fine. But when you actually run it in production, the whole point of Spark is that you can run a data set that's large, so large that it doesn't fit in memory on one machine, that you need a whole distributed system to write it. So when you have a data set that's big and you call collect on it, you're now going to trigger this out-of-memory error. So the general rule of thumb is when you call collect on a large RDD, you can trigger an out-of-memory error. So that means don't call collect on a large RDD. And in fact, it's worse than that. You want to be cautious with all actions that may return unbounded output. So if you think about the particular action, if you think about how much data it's going to return, and it's scaling up and growing with the same speed as when your RDD grows, then those actions you want to be really careful with. So they include count by key, count by value, and collect by map. Instead, you should do something else. So your first option is choose an action that returns a bounded amount of output per partition, such as count or take n. So maybe in this case, we just wanted to kind of sanity check, call some kind of action to make our RDD actually do the transforms. Count will be sufficient to do that, or maybe take, just so that we can get a few of the sample sizes out. But there are cases when we really do want all the values in the RDD. And so for that, you need to choose an action that outputs directly from the workers and doesn't send the data back to the driver. So one such as command is save as text file. Save as text file, each of the individual worker nodes will take all the data in their partitions and write that out to a file without sending it back to the driver. Okay, and with that, I'm going to send it over to Holden, who's going to finish the talk.
So Hadoop writables, like other input formats as well, this can be a problem, right? Because these types aren't serializable by Java, and if we want to work with stuff in Spark, it needs to be Java serializable. They provide their own serialization mechanism, but we can't really use that. So the solution to that is when we read our data in, it's important to do what's called a narrow transformation right afterwards. And narrow transformations don't involve a shuffle, so we don't have to send stuff over the network. A simple example of that is we can just read our data in, do a map, and convert it from the Hadoop writable type into a native type, like a Scala case class or a standard Java serializable type. Another sort of common serialization error that a lot of people seem to experience is when they accidentally capture a non-serializable object in their closure. And this can happen mostly when we reference a field inside of an object. Once we reference the field, we're going to grab the entire object and have to try and serialize that. And the solution to that is we're just going to go ahead and capture the serializable parts locally. Another one is network connections, and I think most of us understand that network connections aren't serializable on their own. But a common sort of place where this happens is when you're creating connections to things like Elasticsearch, or you're creating Jetty clients or other things which have network connections underneath the hood, and then we accidentally try and serialize them and use them inside of our closure because we want to reuse our connection. And the solution to that is we can just create the connection on the worker. And I'll show how to do this later in some code samples so that we can reuse the connection for multiple records. But so sort of the most common serialization error that I see happen on the mailing list and when I'm talking with people is referencing fields on non-serializable objects. And that's just what's happening here. And the solution to that is we're just going to make a local copy of that field. So we'll just have a val or just a standard variable with just the data that we need that's serializable and reference that in our closure. Yeah. And it'll also be faster too than if we fixed the other object and made it serializable, because we'd be trying to transfer additional information that we didn't need. So it's 2 for 1, faster and works. Another thing which doesn't always work, another thing which doesn't work is when you try and access RDDs inside of transformations on other RDDs. And I do this a lot sometimes just out of functional habit because I'm used to writing maps inside of maps. It's pretty convenient, but it doesn't really work in Spark. So a really common one is when we're going to do a map followed by getting the key from another RDD. And instead of that, we can just join these 2 RDDs together, and then we can just map over the result. Sort of another one is the map inside of the map, and that's the one which I tend to write when I haven't had enough coffee in the morning. And the solution to that is we can actually just do the Cartesian product in Spark, and then we can map over that. And there's other cases like this, but it's important to remember that only the driver program can cause transformations or actions on RDDs, and we can't do it inside of other things that are executing on the workers. So another thing that's important is writing our data out, right? And if we're writing it out to something where there's already a Hadoop output format, we can just go ahead and use that. But maybe we have a legacy database system that we want to interact with, which doesn't have a Hadoop output format for us to work with. So there's sort of really 2 options. There's the DIY approach, and I'm wearing a DIY skirt today, and it's a little ugly, but the DIY approach for writing stuff out to databases isn't nearly as ugly as my skirt. And so we can use for each partitions to reuse our database connections in sort of the DIY approach, and I'll show a code sample with this. The other option is if our database happens to speak JDBC, we can use the Hadoop output format, DBOutput Format. And that's kind of cheating, but it's better when you can use other people's code. I'm really lazy. And if your database vendor has their own Hadoop output format or connector, go ahead and just use that one instead, right? There's no need to write custom code. That's just the path of sadness. So, okay, this is the first cat picture because Vida took all of the cat pictures I tried to put into her parts of the slides out, and I really like cats. But there is some value in this cat picture. This cat is wearing a DIY hat, and we can see that the DIY hat is functional. It keeps the cat warm and a little bit angry. And so, the DIY approach totally works. It might not always look the prettiest, but it's really functional. So, the DIY approach for writing our stuff out to the database is we're going to use this thing called for each partition. Now, how many people have heard of map partitions? Okay, cool. That's pretty cool. So for each partition is really similar to map partitions. It gives us an iterator with all of the elements for each partition. Except instead of map partitions, which is a transformation, it's an action. So it causes evaluation. So we don't have to worry about Spark re-executing our write out to database step if we later call collect on the same RDD again or something like that. So for each partition is what you should be using instead of map partitions for things like actions that are writing data out. Here we're using the wonderful Happy database, which is very vendor neutral. If there is a Happy database, my apologies, this constructor is not valid. But we're going to create our connection, and we're going to be able to reuse that connection for all of our records. And then we can either write the records out individually, or if our database has some sort of batch update thing, you should go ahead and do that instead, right? There's no point in generating extra network traffic that you don't have to. Cool. So the other option is DBOutput Format, which works with JDBC-based databases. So we have a cat record because, I like cats. And sort of the important things that we need to do is we need to tell it which fields are going to actually get written out into which positions. So here we have our custom write function. We also need to define a read function for this to compile, but it can just be null because we're not actually going to use it. But I left it out so the code would fit on a slide. So we just have this custom write function, and we set string, and we set int, and that's just because there's different types that we're going to write out. And then we have the corresponding table names in this array down here. We have to create a job conf object because this is sort of one of the more traditional Hadoop ones that we don't have wrapped nicely inside of the Spark context. So like some other output formats like sequence files, we sort of hide this whole messing with the job conf thing from you. But for custom ones, you need to go ahead and do this. So we create our connection, we set the table names and what our fields are, and we write the data out. And hopefully your database stays up when all your workers try and write data to it. Good luck. The same consideration applies to for each RDD, but you can really easily put a sleep in there. So, it's kind of hacky, but it works. Okay, let's go away from hacky things and look at happy, fun things that are awesome. We're going to look at reusing our code. How many people use Spark streaming right now? Cool. Okay, so not too many yet, and I hope the rest of you start using Spark streaming soon. So this is going to be awesome. You're going to take your batch jobs that you've written and reuse them in streaming. The really easy thing is this function called transform. And transform just lets us reuse the transformations that we've written for working with RDDs on DStreams, which are Spark's way of representing streaming data. Now, DStreams have a really similar API to RDDs, so sometimes people try and copy and paste their code over, which is a little ugly and tends to not work completely. So instead, what we should do is use transform when we're wanting to reuse RDD to RDD transformations, or use for each RDD when we want to reuse output operations that we've written for our batch processing. With for each RDD, we also get some time information. In this case, I'm not using it. I'm just throwing it out and writing my tweets back to Elasticsearch. But if you wanted to write them out to different data stores or into different directories based on the time, we could use this time information here. Okay, so we're near the end, and thank you for staying with us on Friday, really. I promise there is another picture of a cat, and if we don't run out of time, there's some bonus pictures of cats at the end. You should hang around for the bonus pictures. And all of these cats are commercially licensed. It's really important to me, and you've noticed some of the Flickr credits. Okay, more seriously, we're going to cover how to factor our code so that we can do unit testing of our code, because a lot of times in Spark, we write these Lambda functions that are really convenient, but maybe not the easiest to test. Then we're also going to cover how to test more than just the functions we're writing, but also how to test our transformations on our RDDs. Now that's great, and for the few of you who had your hands up for streaming, or for the rest of you who are soon going home and writing your streaming apps, we're going to talk about some of the special considerations for testing streaming code. Kitty! Okay. Is that cat's... You're all that cat. You're all sleepy. That's good. Okay. Sorry, I digress. So simple unit testing, right? So this is a really common pattern in Spark, is we write our transformations and we do these sort of inline functions, which are really fast and really easy to write. But if we're going to start putting complex business logic in them, we should consider factoring them out into functions like this parseLine function here. And then we can just use Scala or Java or whatever testing frameworks you're more familiar with, and just write our tests regularly. And this is great and easy and doesn't involve having to include any additional libraries. It's really simple. It costs you nothing. The other option is we want to actually test the entire workflow of our program, right? If our functions are correct, but our transformations are completely screwy, it's not going to do us a lot of good. So to do that, we're going to need to create some RDDs, and to do that, we're going to need a Spark context. And this you can sort of just skim. This is a trait. It provides a Spark context to us. But the really important thing to take away from this, if you're going to go home and start writing some more tests, and I hope you all do, tests are awesome, is instead of stopping our Spark context by calling sc.stop, we go ahead and call local Spark context.stop. And sc.stop is what you should normally be doing, but in your cleanup function on tests, local Spark context.stop will not only stop the Spark context itself, it'll also reset some properties on the configuration. So the next test that's going to go ahead and run with another Spark context isn't going to try and bind to the same ports. And so sometimes you can end up with like really weird, results in Jenkins if you don't do this. Now, you could have written that code or taken pictures, as I see some people are doing, or you could go to sparkpackages.org. Who's heard of Spark packages? Okay, almost everyone. But for those of you who don't know about Spark packages, it's a really wonderful resource. There's a lot of code on there, and it's all related to Spark, and it's really easy to include in your programs. So there's a Spark testing base package. It has 1 vote so far. I'm hoping that changes after this talk, hopefully positive votes. But you can go ahead and get this Spark testing base, and it'll provide that trait for you that I was showing on the previous screen. Yeah. Cool. So we've included our testing base, or we've manually created our Spark context, and we want to go ahead and actually write some tests now, which is great. Just including frameworks doesn't do a lot. So testing that we should parse some stuff with CSVs. We parallelize an input. That's just a really convenient way to write our input data in our program. We could totally still use sc.text file and reference a local file, but I like using parallelize when I'm doing my unit tests if they're small enough. Our result is just a standard map, and then we call collect, which, despite Vida's warnings, is totally fine to do most of the time in unit testing. If you have too much data that you can't call collect in unit testing, you should revisit your unit tests and maybe consider if these should be integration tests, right? Because generally our unit tests are running on a single box. So we just use collect, and then, here I'm using should equal, but you can use whatever assertion frameworks you want to use for testing. There's nothing magic about should equal. So, we can now test our regular batch processes with Spark, which is pretty good, right? That's useful. But now we want to go ahead and test our streaming programs. So there's a few challenges for that, right? The first one is we need to create some streaming data to test against, right? And we probably don't want to spin up Kafka as part of our unit tests. That's the path of madness and sadness. Another thing that we need to do is we need to bring our data back into a place where we can actually compare it and make sure it's correct. We don't have really collect on DStreams for doing this. So instead, we're going to use for each RDD, which I introduced to you briefly as something we can use to reuse actions, but we can also use it for arbitrary code on DStreams that we want to operate on a per time slice window. So we're going to use for each RDD to collect our information. And the last sort of consideration that is special to Spark streaming is we have to figure out when we're done, right? In normal Spark, we're done when we've processed our data. But in Spark streaming, when we've processed our data is a little more loosey-goosey. So there's 2 ways to do this, or 2 that I remember. One of them is we can override the clock that Spark streaming uses and do a bunch of magic in there, and it's a little ugly, but it works and it's reliable. The other option is this less ugly approach. In some ways, we can use a timeout. And the downside of that is it's a little slow and quite possibly flaky, right? If your server randomly slows down a bunch, using timeouts is not going to be happy. So I cheated and I didn't provide the code to do that for you. If you're interested in that code, the code which addresses all of those issues, you can go look in the Spark testing base package, and please upvote. Oh no, it's not the end yet, sorry. So you can go and look at that code, and it addresses all of these issues, and then we can actually just go ahead and write this. And the reason I didn't put that code on a slide is it doesn't fit on a slide, not even 6. But just use the package, and then you can write your tests like this. And so this test, I think, is really cool, right? Like, I mean, maybe I'm kind of a nerd because I'm getting excited about tests, but I'm really excited that I was able to write my input, my expected output, and then just do test operation and have that actually like test some streaming stuff for me. I'm excited about this. And so let's look at test operation. We're providing it the type information about what our input types and our output types are. We're giving it our input data, and the tokenized thing in teal is actually some mysterious function which tokenizes our strings, but this tokenized function is actually operating on DStreams. And so this is actually like our streaming function that we're going to be testing. We provide it with our expected output, and then I say use set equals true, and this is mostly because like I don't particularly want to worry about ordering inside of each time slice. So the other thing to notice is that our input data here, each of these lists inside of the input data represents the input data for that time slice. And this is actually maybe not a great example in retrospect, because we could have multiple pieces of input data in each time slice, but for the sake of fitting it on a slide, I didn't do that. And our output data, more clearly illustrates that we can have multiple values coming back on each time slice. Cool. And so that's the end, but I did promise that there were going to be bonus cat pictures, and so I'm going to go ahead and show you some bonus cat pictures. This cat is my friend's cat, and it's sleeping. This is another cat. And that's a dog. Okay. Yeah, so let's go back to the end slide, and do we want to take questions? Or to...
We could.